Hi and welcome back. Welcome to this lecture on the execution architecture. Now in this lecture I'll have a look at just what an execution architecture is, what it's supposed to be achieving as opposed to the conceptual architecture, for example. What does it enable and help to bring about? What are the elements within an execution architecture? What are some of the notations that we use within a component diagram, for example, of an execution architecture to indicate the things that are of interest to us? And then we'll have a look at aggregating some of the objects into useful components or subsystems to achieve some of the qualities we want. Then we'll have a look at evaluating an architecture, because that seems to be a fairly important part of it all. Now we'll start from reviewing what you already know. You already know the architecture context. We've already been through that, and by now you probably will have a pretty good grasp of what the context is that this architecture is being developed in, and what context that the whole thing will have to satisfy. You also know the constraints that you're working under and the risks that you're dealing with. So you should have by now a fairly good handle on just how this project is progressing. The other thing you should know, or you will need to know before you can do much in the way of an execution architecture, is you should have a good, sound theoretical model of the proposed solution. This is the conceptual architecture. It is a theoretical model. It should enable all of the functionality that's needed, but it ignores any of the implementation consequences of turning it into a computer system. I mean, it really is a theoretical system. Now, in the execution architecture, you have to transform that theoretical architecture into a computer system, with all the constraints that a computer system has on it, the imperfections that it imposes simply because it is a physical system, and some of the things that need to be put in simply because it is a computer system operating in the world. So while we try to do that, we have to do it without without compromising the theoretical solution we came up with. It probably will get a little bit distorted, but we have to maintain fidelity with it. We can't drop functions. We can't radically transform functions. We can't suddenly just say, well, you can't have that, you're going to have something else. We have a good theoretical answer, and we want to transform that into a computer system with as great a fidelity as we can.